Unit 3, Part 1. Unit 3 is Computing Truth Values, is the title of the chapter. But very crucially, this chapter introduces you to the notion of truth functionality, and it shows you how to prove that a certain operator is not truth functional. And that's, I agree with Klenk when she says it's the best way to really understand, to get clear on what it means for an operator to be truth functional. And I'm going to be starting with that, even though that's the explicit topic only of sections 3 and 4, the last two sections of the chapter. But it introduces you to truth functionality, and it gives you the tables, the truth tables for our 5 operators which get symbols. As we discussed in Unit 2, right, there's a special set of English sentential operators, right, blank and blank. What is a sentential operator? Sentential operator is an expression containing blanks such that if you substitute sentences into the blanks, you get more sentences. So it's what you build or construct sentences with. Special set of English sentences, blank and blank. That's first, blank or blank, not blank, blank if and only if blank, and if blank, then blank. Those sentential operators are the ones receiving symbols. They're the ones whose structure we present formally in our system of sentential logic. They are the special symbols because they have the special, those sentential operators get symbols, whereas the others don't, as I talked about in Unit 2. That set of 5 sentential operators get symbols because they are truth functional sentential operators. What does that mean? Okay, so, and this is the crucial definition, and what I'll be doing first few parts is giving you a few, showing you how to prove that a sentential operator is not truth functional. So the ones, I'll give you the examples of Steve believes that P, that's a sentential operator. That is a sentential operator. Or Steve believes that blank, sentential operator. Blank after blank, P after Q, that's a sentential operator. I'll show you how to prove that these are non-sentential operators here. And as I said, that will definitely be a question in your exam. Prove that a certain sentential operator is not truth functional. Okay, so what is truth functionality? A sentential operator, a sentential operator is truth functional if the truth value of the sentence constructed with this operator is determined entirely by the truth value of the component sentences. Okay, so you're familiar with the idea of a function, right? That's one thing determining something else, right? Y is a function of x, right? Y equals fx, right? For example, y equals 2x. It means if I give you the value of x, you can determine the value of y. Or if I give you some specific value of x, the value of y is determined, right? So that's what a function is, one thing determining another. Now, we talk about the truth values of, in the definition of truth functionality, I had the truth value of the compound sentence is determined by the truth value of the component sentences, sentence or sentences, right? The truth value of is what determines and is determined. So the truth value, as I've said before, the truth values for us are merely true or false. Every sentence has a truth value, and that truth value is either true or false. Okay, so what it means, okay, take an example like not, right, or and, right? In this Unit 3, you're presented with the truth tables for these 5 sentential operators. It is the truth functionality of these operators which makes the truth table possible. So in these examples I'll run through, I've got the truth table for not P. Here it'll be the truth table for and, P and Q, right? And I've got next to it Steve believes that P, and here P after Q, these two operators, right, Steve believes that blank, blank after blank, those two sentential operators are non-truth functional. What that's going to mean is you cannot actually fill a truth table. You cannot actually construct a truth table from for these operators, right? So I'm putting this here to contrast with these. We won't actually be able to put values in. That's what I will show you, that you can't put values there. But it is because the operators we do symbolize, not P and Q, is because they are truth functional that we can have a truth table, right? It is their truth functionality, the truth functionality of those five operators, which makes a truth table for them possible. So what do I mean? Consider and, all right? The English word and. It's a sentential operator. You build sentences with it, blank and blank. Fill in any sentences. What does that word mean, right? And more specifically, what determines whether that sentence is true or false? Okay, as speakers of English, you know what and means. When I say blank and blank, what am I telling you? I'm always telling you that these two things are true, right? Now, and, the sentential operator, and, is truth functional because the only thing that goes into determining the truth value of any blank and blank sentence, the only thing that goes into determining the truth value of that sentence, whether that sentence is true or false, is the truth value of the component sentences, right? Here, the emphasis on the truth value of the component sentences. That means the meanings of the sentences, what they actually mean, doesn't matter, right? It means if I give you merely the truth value of those component sentences and nothing else about those sentences, you have enough information to tell me whether the blank and blank sentence is true or false, right? So there are an infinite number of sentences we can construct with the sentential operator and, right? But for all of them, it is the case that if both of the component sentences are true, right? So we can construct an infinite number of sentences with the and sentential operator, right? What we have to do is plug in two sentences and we construct a compound sentence, a conjunction, right? Now, for every single sentence we build where the two component sentences, the two sentences we plug in, every single time that those two sentences are true, right, for that infinite set of sentences where both of them are true, the conjunction is itself true, right, for every single set. Whenever both P and Q are true, P and Q is also true, right? The truth value of P and Q is determined entirely merely by the truth value of P and Q, right? When they're both true, right, there is a function, and that's the arrow that we can draw, right? Given merely the truth value of P and Q, if I'm told that they're both true, I know that P and Q is true, right? This first row on this truth table, and this is true of every row, but this first row on a truth table symbolizes an infinite number of possible sentences, right? There's an infinite number of sentences where of and sentences. There's an infinite number of conjunctions where the two conjuncts are true, right? 2 plus 2 equals 4 is true, right? Just list a whole bunch of true sentences. They all sort of fit into this first row. But the point is, in saying this is a truth functional sentential operator, the difference in all those sentences doesn't matter. It doesn't matter for determining the truth value of the conjunction. The only thing that matters, the only thing that goes into determining whether P and Q is true is the truth value of the component sentences.